Next topic is monochromatic plane wave. The first thing is monochromatic. Monochromatic means the light which has a single color. This is a plane wave. A plane wave may be defined as if the phase of the wave, if the phase of the wave is same for all the points on a plane surface. Is known as plane wave. What is plane wave? I have written if the phase of the wave is same for all the points on a plane surface is known as plane wave. And what is uniform plane wave? If the phase of a wave is same, if the phase of a wave is same for all the points on a plane surface, having the having a constant amplitude is called uniform plane wave. Suppose a wave is traveling in the z direction. We have considered that a wave is moving in the z direction and there is no dependence of x and y. Because the wave is only, we have specified that the wave is moving in the z direction. Then x and y, there is no dependence. Here, the fields are uniform over every plane perpendicular to the direction of propagation. So, fields are, we must specify the fields. The electric field must be equal to this. The magnetic field must be equal to this. And this E naught delta, which is equal to E naught e to the power iota delta, and B naught delta, which is equal to B naught e to the power iota delta. Here, Maxwell equations impose extra condition on E naught and B naught as what the condition are: the divergence of electric field is equal to 0 and the divergence of magnetic field is equal to 0. How we can prove that the divergence of electric field and the divergence of magnetic field are 0? Then it follows that we will consider divergence of electric field. We know the divergence partial divided by partial x, x component partial divided by partial y, y component. We know about this. This is the dot product, this is the dot product, and the electric field, we have the electric field, this one. So this is the electric field. And now we must multiply this term with partial divided by partial x, this and this. When we differentiate partial divided by partial x, there is no x dependent, this will be equal to 0. Partial divided by partial y, there is no y dependence, this will be equal to 0. And there is only the z dependence, because the wave is propagating in the z direction, then we must have iota k when we differentiate this, and the same term s. Now, this is the relation, and we need to get 0 here. How we can get 0? Because we need for the divergence of E is equal to 0. Here, this term, exponential of this term is not equal to 0. Iota is not equal to 0. K is not equal to 0. All these three terms are not equal to 0. So what is the factor? Then this multiply with these terms, and we can get 0. The only term is this one, because E naught z, if a wave is propagating in the z direction, then it means that the electric field is oscillating in the x direction or in the y direction. So it means that in the electric field in the z direction will be equal to 0. There will be no z direction of the electric field. So we must, E naught z must be equal to 0. If this is equal to 0, the whole term will be equal to 0. We must take this term, because if a wave is moving in the z direction, then the electric field will not oscillating in the z direction. It will oscillating perpendicular to the direction of propagation. And similarly, the same case we can show for the divergence of B. We will put the same process we have, and B naught Z will not be equal to, will be equal to 0, because the B component will not oscillate, or will not be oscillating along the propagation of wave. It will also oscillating perpendicular to the direction of propagation. So it means that the electromagnetic wave are transverse wave. This is the point that we are looking for, that the electromagnetic waves are transverse waves. Similarly, using Faraday's law, del cross E, which is equal to minus partial B divided by partial T, then how to find del cross E? We know the method of determinant. We will write x, y, and z, the unit vectors, and del partial divided by partial x, y, and z, and also the electric field, the Ex, E naught y, and E naught z. And at the right hand side, minus partial divided by partial b naught x this one, b naught y this, and b naught y this. And then using the standard method, we will ignore this column and this row, we will get this, and then minus y, we will ignore this, and this, we will get this. This is the rule of determinant. And then which is equal to differentiate this, and this with respect to time separately. Then we can get b naught x iota omega x, b naught y iota omega y, plus b naught z iota omega z, and I can take this term common. Further, if you look this expression, we can cancel this term and this term. Also, we have the iota term, which is also common, and we can cancel out this. And then we have a simple equation, minus E naught tilde k x plus E naught x k y, which is equal to B naught x omega and B naught y omega y. And also we have the term plus B naught z omega in the z direction. But by comparison, the left hand side and the right hand side with the unit vector x, so we have x, we can get this, and y we can get this, and there are no z component. So it is equal to 0. Now, in compact form, this equation may be written like this. How this is possible? B naught x, which is equal to k divided, I have written this in a compact form, z into E naught. Here, the electric field and magnetic field are in phase and mutually perpendicular. Then B naught e to the power iota delta B, which is equal to k divided by omega e to the power iota delta E, the phase of electric field and the phase of magnetic field, they are in phase. Then after removing the tilde, we can use e to the power iota delta B, because this is the phase term. And whenever the phase are equal, then we can get beta, which is equal to k divided by omega E naught. We also know from the previous knowledge omega, which is equal to kV. We have this equation. Now we are working in the light electromagnetic wave. Then we can say that omega, which is equal to kc. If we put the value of omega, which is equal to kc, then k and k will cancel out, and we can get B naught, which is equal to 1 over c E naught. Now, propagation in any arbitrary direction. If we consider the uh, the the propagation of electromagnetic wave in any arbitrary direction, then k is the propagation vector, k dot are appropriate generalization of kz we can put. Uh, if we put, then E field, which is equal to E naught e to the power, we can replace kz with k dot r, and this n is the unit vector, and then B can be equal to 1 over c E naught, because we have find out B naught, which is equal to 1 over c E naught, and then e to the power this, and this is the k cross n. And then we may write B, the magnetic field, which is equal to 1 over c k cross E. If we put the value of this one, then this is E, then we can write like this. Now the actual electric and magnetic fields in a monochromatic plane wave with the propagation vector k and polarization n. Finally, we can, because this is the actual electric field, E naught cosine of k dot r minus omega t plus some phase constant, and n is the unit vector, and B we can also represent 1 over c E naught cosine of this and k cross n. So this is the monochromatic plane wave, which is a transverse wave.